Hi there. We talked today in class about disk method and washer method, and I showed an animation illustrating what we're doing because it's a little hard to conceptualize when you first are learning about it. That animation came off of washer method demo gallery. And if you type that into Google and search, it'll be the first one that pops up. And I showed the first link, and I clicked on animation under partition/washer. Partition/washer. And it just gives you a picture of what we're doing, because 6.2, we're taking our curve that we've been calculating, right? We have our XY coordinate, and we've been calculating the area contained, for example, between two curves as follows. And we're taking that region, and rather than just calculate the area, upper minus lower, we're going to say, well, what if we took that area and we rotated it, we spun it around an axis of revolution? And today we focused on the x-axis, right? If we took that area and spun it around our x-axis. And it makes, in the end, kind of this washer look, right? Like a washer you stick on a screw. And a washer is made up of two circles, okay? Our inside circle has a small radius, and our outside circle has a big radius, and we call those big R and little r. Okay? And we use those to calculate area. Right? Area of a circle, just as a reminder, is pi r squared. And so in this particular case, we have pi, our big circle, so big R squared, and then we're going to subtract our little r, right? Because there's this middle circle that's been removed from the total area. But now this one washer that you see in your animation, if you go to this website, this one washer is just a piece of that total area, and I want to know what happens when I spin the total area around the x-axis, not just one little rectangular portion. Okay, well, if I take this rectangular portion and spin it, and the one next to it and spin it, and the one next to it, and do that for every infinitesimally small rectangle, I end up with my integral from A, this is A, to B, if this is B, okay, of pi r squared, big R squared minus little r squared. And these are going to be measurements of x, so I could put in, for example, r of x, and so we have dx. And essentially, that's where we derive these two methods. So we have some vocabulary. A solid of revolution is what we're talking about, right? It's the region that's revolved about a line. Our axis of revolution, and I shorthanded, or we shorthanded AOR, the line about which a solid of revolution has been formed, right? So in this particular example, when we were spinning it around our x-axis is the axis of revolution. Okay. A disk is formed when you're revolving a rectangle about an x-axis about an axis adjacent to one side of the rectangle, which simply means this region that we're calculating would be attached to our axis of revolution. Okay. And what that looks like is this washer, but with no hole, because there's no separation between this region as it spins around the x-axis. There's no separation between that region and the axis of revolution itself. And so it's spin around the x-axis, no hole. And that would be a disk, as opposed to a washer, which is a solid of revolution with a hole. So disk method and washer method inherently are the same equation. Right? We have here disk method is pi big R squared. Washer method is pi big R squared minus little r squared. But remember, disk method is just a region with no hole. And so if we were trying to find our little r, for something that has no whole, well, what would be our little r? 0. And so 0 squared, you're minusing 0, which is nothing, and that's how we get this disk method. And so you actually can use washer method or the idea of washer method in finding the region of a disk, but just remember your little r is 0 because it's attached to the axis of revolution. Okay, so number 1, we're finding the volume of the solid with the given boundaries and axis of revolution. Again, this worksheet is uploaded to my website. Download it. Fill it out along with me. I challenge you to stop the video. Maybe after we do number 1, stop it. Try number 2 on your own. If you get a little stuck, turn the video back on. Allow me to provide some guidance for getting you through that stuck spot, and then turn it off again. Try it a little bit more. Or if you can complete the problem, turn the video back on when you're ready to check your answer. Okay, and continue to do so. Number 1 and number 3 are a little bit different, so those might be ones I at least watch the beginning of, and then as I'm getting the hang of it, pause it. Okay, so number 1, find the volume. Our boundaries, we're going to start with graphing it. Okay, so if you graph y equals root x, okay, so y equals root x, and y equals 0, you can put that into your calculator if you want, but remember that's just the x-axis. And x equals 3, which we are not going to graph, it's a vertical line at x equals 3. And we're going to be spinning it around y equals 0, which remember is the x-axis. Okay, so really in my calculator I'm just going to graph the root x. And my window is going to go from -5 to 5. So our graph is going to look like this. Okay, so this is our y equals root x. We have a vertical line at x equals 3. That forms a boundary. And then we have another boundary here with the x-axis, y equals 0. And so what's the region bounded by those 3 places? Right here. And that's the region we're going to be spinning. Sorry, that's the region we're going to be spinning. And so we have our integral pi r squared, don't forget the pi. Our bounds go from 0 over to the vertical line, which is at x equals 3. My big R is going to be the distance from my axis of revolution to the farthest point on the graph that I can touch, or the farthest point of the shaded region I can touch. In this particular case, because we are revolving around the x-axis, we're going to draw our representative rectangle towards the x-axis. Even if it can't touch, as you'll see in later problems, it's still going to be drawn towards the x-axis. And our final integral is going to be all in terms of x, right, dx, since we're revolving around the x-axis. Or, as you'll see in later lessons, when you revolve around y equals 3, it's going to be the same thing, right, towards that line. So it's going to be towards x, or it's essentially going to be oriented towards x. So it's going to be dx. Okay, so my big R, distance from axis of revolution to the furthest point of the shaded region. And that furthest point of the shaded region is this graph here, y equals root x. And so I'm going to be doing root x squared minus my little r squared. And my little r is the distance from the axis of revolution to the closest point of the shaded region, which in this case there is no distance between the axis of revolution to the closest point, because the axis of revolution is the closest point. It's attached to the shaded region. It's a lower boundary. And so since there's no distance, my small r is 0. And yes, this is disk method, right? I'm showing that washer method could technically be used. It's essentially the same thing. All right, so we have pi. Clean this up a little bit. 0 to 3. Root x squared is x minus 0 is just x. So we have pi, power rule, 1/2 x squared 0 to 3, which is 9 pi over 2. Okay, number 2. This might be the one I challenge you to turn the video off for a bit or pause it, try it on your own. Okay, we're going to go ahead and graph it. So we graph our square root 16 minus x squared. And our x-axis, which is y equals 0. And so my region looks like this. It's a semicircle. Okay, and so I'm going to find my bounds. My bounds are where this semicircle touches the x-axis, right, because it's bounded by y equals in the x-axis. Don't forget the pi. And so this left intersection point is at -4, right? Because if it's an intersection point, then root 16 minus x squared has to be equal to 0. Well, what makes this equal 0? Well, 4 does, because 16 minus 4 squared is 0. And -4 does. So those are our bounds, -4 to 4. And then we have our big R. So representative rectangle. Our big R, distance from our axis of revolution to our function. Okay, so axis of revolution to function is the function itself, which is root 16 minus x squared squared minus my small r, which is the distance from the axis of revolution to the closest point, which is no distance because it's attached. So then we get pi, let's clean it up a little bit, -4 to 4. Square root of 16 minus x squared squared is 16 minus x squared minus 0, which is pi, power rule, 16x minus 1/3 x cubed. And so we get pi, 16 times 4 is 64, minus 64 over 3, minus our, plug in -4, negative 64, plus 64 over 3, which all of that, when you solve, should give us 256 pi over 3. Okay, so we are on to number 3. Number 3, we are finding the volume of the solid with the given boundaries and axis of revolution, and this actually is a typo. Okay, and so we have y equals 2x squared, y equals 8, and we're revolving around y equals 0, which is the x-axis. Okay, so graph it. We have our y equals 2x squared. We have our y equals 8. Just this region. We're going to be revolving it around the x-axis. Okay, so we're finding our pi integral. What are our limits, lower and upper, our bounds, right? So the intersection point of 2x squared and 8, so where does 2x squared equal 8? Or again, you could use the intersection button on your calculator. Well, that would be where x squared equals 4, because I divide the 2 over, which is x equals plus or minus 2. So we're at -2 and +2. Representative rectangle, so here's where we have to use washer method because our representative rectangle doesn't go all the way down to the axis of revolution. It does right here at the center, but it doesn't over the whole region. And so my representative rectangle, I need to figure out first, what is that big R? What's the distance from the axis of revolution up to the furthest point of my shaded region? That distance from here up to that furthest point is this graph, this horizontal graph, which is y equals 8. And so we're going to do 8 squared minus our lower, or a small r I should say, and our small r is the distance from the axis of revolution to that closest point, right? What's the distance from the axis of revolution to there? Well, that's this lower graph, which is our 2x squared. And square it, right? Pi r squared, area of a circle, dx. Okay, so we have pi, integral from -2 to 2 of 64 minus 4x to the 4th. So then we have pi, power rule. So we're at 64x minus 4/5 x to the 5th from -2 to 2. When you get that, you get 1024 pi over 5. And you do your f of b minus f of a. Okay, last one, find the volume of the solid with the given boundaries, y equals 2 minus x squared and y equals 1. And we're revolving around the x-axis, which is y equals 0. Okay, so you graph those. We have our y equals 2 minus x squared and y equals 1. We're going to get an upside down parabola and a horizontal line at y equals 1. Okay, so let's go ahead and sketch that. We have our upside down parabola and our horizontal line at x equals 1. Okay, so we're finding this shaded region here. It's the same thing, pi, lower bound, upper bound. So my lower bound is this intersection point, my upper bound is that intersection point. Where does 2 minus x squared equal 1? Okay, so if we do 2 minus x squared equal 1, okay, subtract the 1 over, add the x squared over. We're really asking ourselves, well, where does 2 minus 1 equals 1? Where does x squared equal 1, which is at plus or minus 1? Or, calculator, at 84s you do second calc, 89s you do F5. We're calculating our intersection. They want to know our two curves. You only have two curves in there, right? We put in y equals 2 minus x squared and y equals 1, so that's the only two in there, so it's going to be the first curve, second curve. And lower bound, they're going to want to know something to the left of the intersection point, something to the right of the intersection point. And so our intersection point is at -1, which confirms what we found. Intersection, same thing, first curve, second curve, lower bound, upper bound. And we get 1, which again confirms what we found. So we know our bounds are -1 to 1. And then we need our big R. So axis of revolution, our representative rectangle going towards the axis of revolution. So this is going to be another dx one. Okay, our big R is the distance from the axis of revolution up to that furthest point. Our furthest point is that quadratic, which is our 2 minus x squared squared, minus our small r, which is the distance from the axis of revolution to the closest point, which is the horizontal line, so 1 squared. So we get pi, clean this up a little bit, -1 to 1 of 3 minus 4x squared plus x to the 4th dx, which is pi 3x minus 4/3 x cubed plus 1/5 x to the 5th from -1 to 1. And when you plug that in, f of b minus f of a, you get 56 pi over 15. And there's your answer.